Hello everyone. Today we are diving into the fascinating world of thermodynamics. Have you ever wondered how energy powers chemical reaction or why some chemical reactions feel hot while others feel cold? In this video, we will break it all down into simple and easy to understand concepts that will help you ace your exams and understand chemistry around you. Let's begin with a simple observation. When fuels like methane, cooking gas or coal burn in air, they release chemical energy as heat. But did you know that the same energy can do mechanical works in engines or even generate electricity in devices like dry cells? This ability to transform energy from one form to another is the heart of thermodynamics, the branch of chemistry that studies this energy transformation. Thermodynamics doesn't care how fast or slow these changes happen. It only focuses on the starting state and final state of the system. It only applies to systems in equilibrium where properties like pressure and temperature stay constant. Thermodynamics help us answer questions like how much energy is involved in a reaction, will the reaction happen, how far will it go. To understand thermodynamics better, we need to know some key terms like the system, the surroundings and the boundary. A system is the part of the universe where observations are made, like the reaction happening in a beaker. Everything outside the system is called surroundings. Together, the system and surroundings make up the universe. For practical purpose, the surroundings are limited to the part of universe that can interact with the system. Thermodynamic systems are classified into three types. Open system. Here, energy and matter can freely exchange with the surroundings. For example, a reaction in an open beaker. Closed system. In this case, only energy can be exchanged, not matter. A sealed container like the closed flask is an example. Isolated system. Neither energy nor matter can move in or out. A thermos flask is a great example of this. To describe a system, we use measurable properties like pressure, volume, temperature, and amount of substance. These are called state variable or state functions because their values depend only on the system's state, not the path taken to reach it. Internal energy, represented as U, is the total energy of a system. This includes all forms of energy: chemical, mechanical, electrical, and more. Internal energy changes when heat is transferred, work is done on or by the system, matter enters or leaves the system. Let's take an example. When mechanical or electrical work is done on a system, it leads to change in internal energy. The change is independent of how the work was done. This property makes internal energy a state function. Internal energy can also change when heat is transferred between the system and the surroundings. If we transfer heat without performing any work, the change in internal energy equals the heat exchange. In general case, when both heat transfers and work are involved, the total change in internal energy is given by the equation delta U is equal to Q plus W. This leads us to the first law of thermodynamics. The energy of an isolated system is constant. In simpler terms, energy can change forms, but it is neither created or destroyed. Imagine a cylinder containing 1 mole of an ideal gas with an initial volume Vi and pressure P. If we apply an external pressure Pex, which is greater than the gas pressure, the piston moves inward, reducing the volume to Vf. This movement represents work done on the gas. Let's calculate this work mathematically. The work done W is the product of force and the distance. Since force equals pressure times area and the change in volume is distance times area, we derive the formula W is equal to negative P external into delta V. The negative signs ensure the correct sign convention, that is, the work done on the system is positive. If the external pressure changes in finite steps, the total work done is the sum of all intermediate steps. W is equal to negative summation of P delta V. For reversible process where pressure changes infinitesimally, the work is calculated using integration. W is equal to negative integration of Vi to Vf P delta V. This shaded area under the curve represents the work done. For an ideal gas undergoing isothermal reversible expansion, where PV is equal to nRT, the work done is W is equal to negative 2.303 nRT log Vf by Vi. In free expansion, where the gas expands into vacuum, Px is equal to 0 and no work is done. In real world reaction, we often measure heat as constant pressure. To account for this, we introduce the concept of enthalpy H. H is equal to U plus PV. At constant pressure, the change in enthalpy delta H equals to heat absorbed or released. Delta H is equal to QP. For exothermic reaction, delta H is negative, while for endothermic reaction it is positive. The relationship between enthalpy and internal energy becomes more significant when gases are involved. If delta Ng is the change in the number of moles of gas, then delta H is equal to delta U plus delta Ng RT. This allows us to calculate enthalpy changes even when the number of gas molecules changes. Now let's distinguish between extensive and intensive properties. Extensive properties like volume and internal energy depends on the system size. Intensive properties like temperature and pressures remain constant regardless of size. Ever wondered how we measure the energy changes during chemical or physical process? Calorimetry is an experimental technique that allows us to determine the heat changes involved in a process. The experiment is conducted using a special device called calorimeter, which is immersed in a known volume of liquid. By knowing the heat capacity of both the liquid and the calorimeter, we can calculate the heat evolved by simply measuring the temperature changes. Let's explore how this works under two different conditions, constant volume and constant pressure. Let's start with constant volume. Often done using bomb calorimeter, imagine a steel vessel or bomb surrounded by water to prevent heat loss. Inside this bomb, a combustible substance reacts with pure oxygen. The heat generated during the reaction transfers to the surrounding water, causing a measurable rise in temperature. This setup ensures that the volume remains constant throughout the reaction, and since there is no volume changes, the system performs no work, ideal for energy measurement. We then use the calorimeter's heat capacity to calculate the heat change, denoted as QV, using a simple formula. Now what if we measure the heat change at constant pressure? That's when we use simpler calorimeter setup, often under atmospheric pressure. In this case, the heat change QP is directly linked to the enthalpy change delta H. In exothermic reaction, heat is released to the surrounding, making QP and delta H negative. On the other hand, for endothermic reaction where the system absorbs heat, QP and delta H are positive. This simple yet effective method helps us measure the heat of reaction or enthalpy change, which is crucial for understanding various chemical processes. In a chemical reaction, when reactants transform into product, energy is either absorbed or released. This energy change is called the reaction enthalpy, represented by delta RH. It can be calculated using the formula delta RH is equal to sum of the enthalpy of product minus sum of enthalpy of reactants. For example, take the combustion of methane. CH4 plus 2O2 gives CO2 plus 2H2O. Here, delta RH is determined by subtracting the total enthalpy of reactants from the total enthalpy of product. Reaction enthalpy helps in designing processes like cooling or heating industrial systems. Reaction enthalpy depends on conditions like temperature and pressure. To standardize measurement, scientists use the standard enthalpy of reaction, denoted by delta H. This is the enthalpy change when all substances are in their standard state, that is, in pure forms at 1 bar pressure and typically at 298 Kelvin. For example, the standard state of ethanol is pure liquid ethanol at 298 Kelvin at 1 bar. Phase transformation such as melting or vaporization involves energy change. For instance, ice melting to water at 273 Kelvin requires 6.00 kJ per mole, called the standard enthalpy of fusion. Water boiling at its boiling point requires 40.79 kJ per mole, called the standard enthalpy of vaporization. These processes are endothermic, meaning heat is absorbed. Similarly, the standard enthalpy of sublimation represents the heat required to convert 1 mole of a solid directly into vapor. For example, dry ice sublimes at 195 Kelvin with standard enthalpy of sublimation is equal to 25.2 kJ per mole. The magnitude of enthalpy change depends on the strength of intermolecular forces. For example, water molecules have strong hydrogen bonds requiring more heat to vaporize compared to acetone, which has weaker dipole-dipole interaction. This difference explains why the standard enthalpy of vaporization for water is higher than that of organic liquid like acetone. Have you ever wondered how we measure energy changes in reaction? Imagine building a molecule from scratch. Using its elements in their purest form, The energy change during this process is known as standard enthalpy of formation. It's defined as the heat change when 1 mole of a compound is formed from its elements in their most stable states under standard condition, that is 25 degrees Celsius and 1 bar pressure. For example, hydrogen gas reacts with oxygen to form water, and in this process, negative 285.8 kJ of energy is released. Similarly, in the formation of methane, negative 74.8 kJ of heat is released. Now let's compare this to a reaction where calcium carbonate forms from calcium oxide and carbon dioxide. This isn't a formation reaction because calcium carbonate is made up from other compounds, not its constituent elements. So, this is an example of a regular reaction enthalpy, not a standard enthalpy of formation. We calculate standard enthalpy of change for reactions like this using the formula delta RH is equal to summation of A delta FH products minus summation of B delta FH. When we write balanced chemical equation with their enthalpy values, we call them thermochemical equation. Remember, the enthalpy change for thermochemical equation depends on the number of moles involved. Now let's explore Hertz's law, which tells us the enthalpy change of a reaction is independent of the path, whether the reaction happen in one step or multiple steps. The total enthalpy change is the sum of individual steps. Standard enthalpy of combustion is the heat released when 1 mole of substance undergo complete combustion with all reactants and products in their standard state. For example, when 1 mole of butane burns, 2568 kJ of heat is released. It's an exothermic reaction which is crucial in applications like cooking and rocketry. Next, let's talk about atomization. The enthalpy of atomization is the heat change that occurs when 1 mole of a substance breaks into individual atoms in gas phase. For example, when methane undergoes atomization, it forms 1 mole of carbon and 4 moles of hydrogen atom. The energy required for this process is 1665 kJ per mole. Bond enthalpy refers to the energy needed to break a bond in a molecule. It is the enthalpy change associated with breaking 1 mole of a specific bond in a molecule. Let's break down methane bond. Each CH bond in methane requires about 416 kJ per mole to break. The total energy to break all 4 CH bond is 1665 kJ per mole. Lattice enthalpy refers to the energy change when 1 mole of an ionic compound dissociates into its ions in the gas phase. To calculate the lattice enthalpy, we use the Born-Haber cycle, which includes steps like sublimation, ionization and electron gain. The total enthalpy change for NaCl is positive 788 kJ per mole. The enthalpy of solution is the energy change when 1 mole of a substance dissolves in a solvent. For NaCl, the lattice enthalpy positive 788 kJ per mole and hydration enthalpy negative 784 kJ per mole combine to give solution enthalpy positive 4 kJ per mole. The enthalpy of dilution is the energy change when more solvent is added to a solution. For example, dissolving HCl in increasing amount of water release more heat, eventually stabilizing at negative 74.85 kJ per mole. In our everyday life, we see natural process happening in a specific direction. Water flows down the hill, heat moves from a hot cup to cooler surroundings, and gases spread out to fill a container. But why do the process occur in just one direction? It's because of spontaneity. Spontaneity means a process can occur on its own without any external help. But don't confuse spontaneity with speed. For instance, when hydrogen and oxygen gases are mixed at room temperature, the reaction to form water is spontaneous but happens very slowly. Spontaneous processes are also irreversible on their own, like water flowing downhill or heat transferring from hot body to a cold one. To reverse them, external energy is required. Many processes like combustion or the formation of ammonia release energy or enthalpy as they occur. This decrease in enthalpy might seem like the driving force for spontaneity. However, some processes like the formation of nitrogen dioxide absorb energy but are still spontaneous. So, while a decrease in enthalpy contributes to spontaneity, it's not the only factor. Now let's talk about entropy, a measure of randomness or disorder in a system. When gases mix or solid melt, the arrangement of molecules becomes more chaotic. Increasing entropy, a spontaneous process often involves an increasing in entropy, especially in isolated systems. For example, when gases mix, the system becomes less predictable and more disordered. Entropy provides another clue about spontaneity. Entropy change delta S is calculated using heat transfer and temperature. When heat is added to a system, it increases randomness, but the effect depends on the system's temperature. Adding heat to a colder system causes a greater change in entropy than adding the same heat to a hotter system. Neither enthalpy or entropy alone can fully predict spontaneity in chemical reactions. That's where Gibbs free energy comes in. It combines both factors. G is equal to H minus Ts. A process is spontaneous if delta G is negative. Gibbs energy is our ultimate criterion for spontaneity, balancing energy and randomness in a system. Let's look at some real life examples of spontaneity. Ice melts at room temperature because of an entropy increase. Combustion of wood is spontaneous and releases heat. Even the slow rusting of iron is a spontaneous process, though it takes time. In an isolated system, energy remains constant, but entropy increases naturally. This is the second law of thermodynamics, explaining why spontaneous exothermic reactions are common. In such reactions, heat released increases disorder in the surrounding. A positive overall entropy change makes the reaction spontaneous. Entropy depends on molecular motion. Higher temperature increases motion on entropy. At absolute zero, the entropy of a pure crystalline substance approaches zero due to perfect order. The third law doesn't apply to solution or supercooled liquids. Free energy change plays a crucial role in understanding chemical reaction. It helps us predict whether a reaction will occur spontaneously and estimate the useful work we can extract from it. Imagine it as a guide that shows us energy landscape or a reaction. Now let's talk about reversible reactions. In thermodynamics, a reversible process means the system stays in perfect balance with its surroundings. In chemistry, reversible reactions are dynamic. They move forward and backward simultaneously, create equilibrium. At equilibrium, the system's free energy is at its lowest. That's why we say delta Rg is equal to 0. But how is free energy related to equilibrium constant? Here's the connection. Delta Rg 0 minus 2.303 RT log K. For exothermic reaction where heat is released, delta RH dash is negative. Their equilibrium constant K is large. This means these reactions tend to go to complete. On the other hand, endothermic reaction with positive delta RH dash have a smaller K value and produce less product. Entropy also plays a role. Positive delta Rs dash makes the reaction more favorable, while negative entropy can hold it back. First, by knowing enthalpy and entropy changes, we can calculate K at different temperatures. This is super useful for industries to optimize product yields. Second, if we measure K in the lab, we can predict how a reaction behaves at other temperature. Thermodynamics truly empowers us to fine-tune chemical process for better efficiency. And that's wrap on the chapter thermodynamics. I hope this video gave you the clarity and confidence you need to ace this topic. Remember, understanding thermodynamics is all about connecting dots and practicing concepts step by step. So don't hesitate to revisit this video whenever you need a quick revision. If you found this video helpful, make sure to like, share and subscribe. For more such concepts and comprehensive explanation, also let me know in comment which chapter or topic you would like me to cover next. Stay curious, keep learning and remember, knowledge is the key to unlocking your future. All the best for your exams and I'll see you in the next video.